But back to MO theory, which is what we talked about last Friday, and there are sort of two last things I wanted to mention now related to MO theory before moving on to the topic of hybridization. Now, before I do that, I'm going to use a couple of videos today, and I'm not going to show you this one, but I just want to mention there's lots of videos that help, animate this stuff, right? So like this is what, so like, oh, okay. Bonding molecular orbital. Anti-bonding. We talked about this last Friday. But look at this animation. I couldn't do that on the board. Watch this.
Anti-bonding molecular orbitals formed by the combination of two 1s orbitals are called sigma 1s and sigma star 1s, respectively.
Kind of remembering stuff now, right, from Friday?
The bonding molecular
oh, look at that.
Is lower in energy than the original atomic orbitals.
That's that kind of animation that you just can't, I can't animate the bonding and anti-bonding. Well, I kind of can with my hands, but there it is. And there's lots and lots of those kinds of videos. I'll show you a couple today related to hybridization because it really does help see these 3D orbitals, right, in their full shape and what's happening. So I highly recommend, especially if you're having like some conceptual questions related to stuff we talked about Friday and today, take a look at some of those videos. Now, where we left off on Friday, before I get to nitric oxide, which has all those different uses in the world and many more, we left off with the homonuclear dimers. That's what we were doing on Friday, right? How do the atomic orbitals come together to make orbitals that are molecular, MOs, right? And we did it for dimers that have the same atom, right? And so we did nitrogen, N2, and we did O2. Right? And so let's do that on the board. And then, because now we're going to start with one that has N and O, heteronuclear dimer, right? Two different atoms. But if I had the same one, remember, this is what it would look like, right? So here would be, say, N2 would, I'm going to just stick with the valence. So the 2s for a nitrogen atom, and the 2p would have, remember, Hund's rule. All right, okay, so that's what the 2p would look like. And then over here, we would have the other atom. This is how we roll when we talk about MOs. And we'd have the 2s over here. And this is how we start. These are my AOs for the two nitrogen atoms, right? This is what we did. We're just getting back in the mood because we had the long weekend. And when we make the MOs, remember we have all those sort of things that we talked about in terms of how these, this difference between the bonding and the anti-bonding orbital, right, is related to the overlap and the same symmetry of the two AOs that come together. Right? So we talked about that. The more overlap, the biggest this delta, Gesundheit, right? And then we also, so that would be filled, this would be filled, right? Sigma 2s, sigma star 2s, right? And then for nitrogen, we also talked about how, oh boy, these are reversed, right? See, I'm now already backwards twice, which is not what I want, okay? And this is the weird thing about nitrogen, because if we go to oxygen, then the way it goes is, you got your 2s in oxygen, okay? And in oxygen, you've got your 6 valence electrons in the 2p. And over here, you've also got the same, okay? And you've also got the 2s. But for oxygen, okay, so those are the sigma star. But for oxygen, we go to the ordering that we usually have, which is that, remember, those pi orbitals have, and this isn't necessarily drawn to scale, but those pi orbitals, right? So this was sigma star, and these are the pi orbitals, pi and pi star, right? Sigma p, right? 2p, 2s, sigma. This would be sigma s, sigma 2s star, sigma 2p. If you want to be exact about it, sigma 2p star. Pi x, pi y, pi x star, pi y star. We talked about all this on Friday. I'm just getting us back in the mood. But the way we left off was that these are, okay, so if I fill these all up now, right? Remember we do the MO filling, then we'd have this, and, ooh, now hold on, yep, this, and there for oxygen. And then over here, we're filling them up. We got those are filled, and this is filled for nitrogen. Remember I showed the movie, pouring liquid oxygen, pouring liquid nitrogen. Oxygen has unpaired electrons, which means it's paramagnetic. It has unpaired electrons, the O2 dimer. This is O2. These are the MOs of O2. These are the atoms. These are the MOs of N2. N2 doesn't have any unpaired electrons, so it's not paramagnetic. But the thing that we left off on, that's what I'm saying, is that these two switch order for those dimers, for lithium through nitrogen. Those two switch order. And we talked about that on Friday. The reason is because for those atoms, these sigma p orbitals can mix in with the sigma s orbitals. And so you get more, because remember, the more overlap, the greater the energy, right? The greater that delta between bonding and antibonding, right? So the more mixing you have, the more spread you get. And it's so much that for those dimers, you push the orbital up. Okay, that's all what we talked about Friday. Now, I got one of each, and I wanted these on the board so that you can see them as we now take one atom from one side and one from the other. It's actually kind of what you expect. You just have to have one thing in mind when you think about NO. So if this is N, okay, over here, and we're going to put 2s there and 2p there, here, 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 here. There's my N atom. And now I've got O over here. So I've got my, but now see the thing is, O is more electronegative. And the way this works for a heteronuclear dimer is, let's write this on the board. So for a heteronuclear, that means that the two atoms are different, okay? But for a heteronuclear dimer, the bonding MOs are closer in energy to the more electronegative atom. Electroneg atom. So what that means is that if I draw my oxygen levels, but you know this, right? You know this also from all the work we did on atoms, right? You know a little something about, remember, this axis is energy. This axis is energy, right? And so if this is 2s for oxygen, and then the 2p's are going to be sort of like here, okay? And we'll fill them up thinking about Hund's rule. Well, now what we're going to have is that the MOs for the NO molecule are going to come closer, they're going to come further down from that side, right? Then they come from that side. You see that? There's an asymmetry. I made it kind of subtle. And why is this curved? That's not good. What's going on here? There's a little bit of an asymmetry here, right? So, so this is lower down. These are lower down, right? So when you draw your orbitals now, oh man, I'm going to draw this a little bit lower, right? So now when you draw them, you see that bonding orbital is going to be closer. You see, this is a bonding orbital still. It's still bonding, right? It's going to be a sigma p, sigma 2p but it's closer in energy to the more electronegative levels. You see that? Right? So it's not symmetric anymore. Okay. And then the same would happen with these guys, right? They'd be closer in energy to the, yeah. They would be closer, and I'm not leaving myself enough room here. That's why I've got some videos. They do it better, right? Okay, we'll leave that one there. It's a little bit better. Not much, but a little bit. So the bond, now, by the way, for NO, let's talk about MO for a second, because there's another thing that's important that we talk about, which is bond order. And, so the bond, electron configuration is another thing, right? So like the configuration, we can write this out, right? So the configuration of, say, O2 would be sigma 2s, right? You're just filling them up with 2 electrons, sigma star 2s with 2 electrons, sigma 2p with 2 electrons, pi 2p with 4 electrons, and then pi 2p star with 2 electrons. That's how that looks. It's a little bit messy, but I hope you can read it. That's just reading up, right? It's the electron configuration of the MOs, just like we would write the SPD electron configuration of atoms, but this is a molecule. Now, sometimes you might, sometimes I would say there's a convention we use, which is that the PZ is the sigma. Nobody can agree on this. So different textbooks say PX, but we're saying if PZ is sigma, then this would be like a sigma 2 PZ, right? And you might, if you really want to write this, you might write that that's pi 2px. If you really want to keep track of it, there's 2 orbitals in there. You didn't fill one orbital with 4 electrons, right? So this would be pi 2px and pi 2py 4, right? That's what's happening in there, okay? Now, but the other thing you can see from the bond, from this filling is also the bond order, right? And so for the bond order, here you would have a half times, and it's all of the, remember, the bond order is all of the bonding electrons minus antibonding electrons divided by 2, right? And if it's 0, it's not a stable molecule. If it's greater than 0, it's stable. And the higher the bond order, the higher the bond strength, right? So that's also from Friday. And so this is 2 minus 2 plus 4 minus 2, and so you get 2. Nope, I missed a 2. Plus 2 plus 4 minus 2. 2 minus 2, that kind of cancels out, right? Plus 2 plus 4 minus 2, all divided by 2. So the bond order for oxygen, now the bond order for NO, bond order for NO is going to be 2.5. Well, it's kind of interesting now. You can see, okay, so NO is stronger, more strongly bound than O2, less strongly bound than N2, and it's kind of interesting. How can I make NO a more strongly bound molecule? Well, I can take an electron away, which is a little bit counterintuitive, right? Because for NO plus, the bond order goes up because the electron that I've taken away was in an antibonding orbital, right? So NO plus actually has a stronger bond than NO, even though it has one less electron. You get this all from just looking at which electrons are occupying which orbitals. In this case, you had, in this very much not drawn to scale, oh boy, figure, right? What you had was one up there. So if I take that out, my bond order increases, right? Okay, all right. And the last point I wanted to make about MO theory before we talk about hybridization is with one other example, and that's HCl. Okay, so for HCl, you got something else happening that's important. So we just talked about electronegativity driving where that this is tilted. Okay, fine. And now we got the fact that chlorine comes into the situation. It's like Chlorine is like, hey, I got 7 electrons, right? And hydrogen is like, hey, I got 1. Now, so how does this work, right? So this gets to what was brought up Friday, which is there's another type of MO. And it's not bonding and it's not antibonding, it's non-bonding. That is not the same as antibonding. Non-bonding doesn't take sides. It just is. Because the way this works is, hydrogen comes at this. Okay, so hydrogen's up here with its 1s. Chlorine is, let's say over here, it's got 3s filled. And it's got, let's draw these, here. Okay, 3p. And chlorine's got 7 electrons in the 3p. Do they all come together and form MOs? No, they can't, because there's only 1 on this side, right? So this 1 orbital will form, let me make myself enough space, so I'm going to exaggerate this a little bit. So this 1 orbital will form a sigma bond, sigma 3p, sigma 3p bond. This would be a sigma 3p star. Now that's exactly what we've already done, right? The sigma, but, oh, there's something a little interesting about this one, right? Because it's an S. It's an S. But that's okay, because the S can talk to a sigma p. We talked about this. The S can talk to this. That's okay, because it's aligned, right? Now, but these guys don't have anyone to talk to. They don't. So they can't make their pi orbitals. They can't do that. And so they just stay there. These stay there exactly at the same place. They're not doing anything different. They're just hanging out. Those electrons are non-bonding. So these are not pi orbitals. Sigma and pi are special names. They refer to these orbitals of the molecule that involve the LCAO, the linear combination of the atomic orbitals. These do not. N, B, N, B. That's what we'll call them. Just to be very clear. Just to be very clear. Now, they're filled. They're filled, and they do not count in the bond order. By the way, this is also a non-bonding orbital. That's a non-bonding orbital. Non-bonding orbitals. These are not going to count. So in the bond order, you have 1/2 times 2 minus 0 equals 1. These do not participate in bonding. I got to fill this. 2 electrons are in that one. Okay? So that's another example of something that happens in these MO diagrams. One of them brought too many electrons to the party. And so there's no one to talk to, but it's okay. They're just going to stay there and wait. Maybe something else will come along. Right? Okay. Now, that is right there what I just drew. Look at that. 2p, 2s, and you get this thing. Right? Oh, that's a beautiful molecular orbital between, okay, fine, it was a 1s and a 3p, but you get the point. It was a p oriented along the axis with sigma symmetry. That means if I look along the axis, sorry, cylindrical symmetry, sigma, means if I look around the axis, everything's the same in a circle, right? Right? So that's a nice sigma orbital between 2 different atoms. MO theory. But see, the other thing that can happen, that is something that I want you to know today, is that orbitals on the exact same atom can also do this. They can also do this. They can combine to form a new orbital. sp, same atom, forms an sp orbital. It's called a hybrid orbital. All right, so we're going to give a couple of examples. This is hybridization. Hybridization. And we give a couple of examples and then why this matters. So this is when 2 or more AOs that are similar in energy. Similar. They're not the same, but they're close. You can't hybridize if one level's way up here and the other level's way down there. But if they're close, 2s, 2p, then those orbitals can combine. And what they do is they combine to form, and this is critical, sets of equivalent orbitals properly oriented. This is really important. That's why I'm writing it all out. Properly, not property. Properly oriented to form bonds. Oh, this is such a big deal, to form bonds. It's the last word there, but I did it all caps to emphasize. Because that's what this is all about. You see, now let's take an example. I'm going to take an example of methane. Who brings what to the party? Okay, I got 4 H's. H, 1S. H, 1S. H, 1S. Okay, this is definitely getting repetitive. I'm going to H, 1S. But I did it. There they are. And they come and they're like, hey, carbon, what you got? And the carbon is like, okay, hold up. I got my 2S, that's here. And I got all my 2Ps. And what are we to do? What are we to do? How can these 4 hydrogens come and bond with the carbon, given that it looks at least like the carbon isn't bringing the kind, how is it going to do this? And also, and this is critical, this is why I wrote it here, properly oriented to form bonds. You see, because this taps into what we learned with Vesper. It does, because Vesper says you got to not repel. Or no, you're repelling, but try to minimize it. Right? That's what's at the core of Vesper. So what this system sees is a way out. And by way out, I mean a way to happiness. And by a way to happiness, I mean a way to lower energy, where all 4 of these can bond to the carbon atom if it has 4 same bonds. If it had 4 same bonds, then it can orient them tetrahedrally and make Vesper happy, minimize repulsions, right? And you get your methane molecule. So what ends up happening is this carbon atom says, hold up, you 4 hydrogens, you wait there. I'm just going to go into the back and do a little reorganization. And I'm going to come in it with, I'm going to say, well, if my carbon atom comes at it with 4 equal orbitals that look like this, those are called sp3 because I took all 3 p orbitals and I mixed them up with my s orbital and I formed equivalent orbitals. Now carbon comes out of the back room and it's like, hydrogens, I'm ready. I can make a minimum energy and I can follow Vesper and we can all have very, very low energy compared to whatever else I could have done if I stuck like that. What I'm really talking about okay, you might know carbon, it doesn't go into the back room. It doesn't, but what is it doing? It's nothing more than solving its Schrodinger equation. That's what this is all about. You just changed the boundary conditions. And so what happened, that's all hybridization is. You're solving the Schrodinger equation all the time. We are always solving the Schrodinger equation. All the time. And in this case, carbon said, well, how can I solve it and minimize my energy with the 4 hydrogens? This gives you the lowest energy. Because now, I got a movie. Now I can make those. See? So I have a picture here. S and those 3, and it says, how can I do it and minimize repulsions? This is how. 4 equivalent orbitals to make it sp3. And this is where I think a movie helps. So I'm going to play this. It's like a minute long.
Each 2s orbital is a 2-lobed shape converging at the nucleus.
There's the 2s.
So there are the 3 2p orbitals. However, When hybridization occurs, the s and p orbitals cease to exist.
They don't cease to exist. They just didn't. It's a new boundary condition. You're solving the equation, right? So just to keep that straight, right?
And the two sp3 orbitals have an entirely different shape.
That's true.
We can see that orbital hybridization explains the VSEPR placement of carbon's 4 valence electrons, since all 4 2sp3 orbitals are equivalent. Each 2sp3 orbital repels the others with equal force, resulting in identical bond angles. The carbon atom only hybridizes when it is in a bonding situation. Here, 4 hydrogen atoms bond to carbon by overlapping their orbitals with carbon's hybrid orbitals. So what would be the reason for this? If we go back and see that both carbon and hydrogen have unpaired electrons, the overlap allows the electrons to pair and thus go to a lower potential energy.
Oh, that's such a beautiful place to stop. Lower potential energy. Happier. That's what this is all about. Okay? So like I said, you can see now the difference, right? If you just watch, it's 1 minute long, and I think it really brings it to life. So if you're, again, want to see this a little bit more conceptually, these movies are good. I have one more movie I'll show you that's like a minute long. Okay, now, the thing is, so what we just did is we did carbon hybridizes to sp3. It's called sp3 because you're bringing 3 p orbitals and mixing them with s to form 4. And that allowed it to do this. But you see, if I had ethane, which is C2H6, it's the same thing. Now, because basically what's happening, a carbon atom comes into this system of ethane and it says, I need 4 bonds that are kind of, equivalent-ish. All right? I got to give 1 to each hydrogen and I got to give 1 to that other carbon over there. And by doing that, it can minimize its energy, it can minimize repulsions, it can be the happiest molecule it can be. But to do that, carbon must have these 4 equivalent sigma-like bonds. It must be able to form those 4 equivalents. So that's very similar to methane, except that in this, so also ethane will be sp3 hybridized. It will have sp3 hybridized orbitals. But then, and you know what's coming, right? So ethane has C2H6, but what if now I've got ethylene? I think maybe I have a picture of it. Do I have a picture of it? Yeah, oh, there it is. Ethylene. Ethylene is used, this tiny molecule is 2 carbons and 4 hydrogens instead of 6. This is used in so many applications I can't possibly list them. Polyethylene is a polymer made out of this as a base. We will polymerize this a little bit later in the semester when we talk about polymers. It's also used in the back of your supermarket, in case you didn't know that. Very soon, actually kind of almost nowish, most of the fruit we get will be super green when it gets here. And then they use ethylene to actually induce, sadly, the ripeness. Doesn't taste as good. But anyway, okay, now, but for ethylene, you've got a different situation, because for ethylene, each carbon atom needs 3 bonds. Each carbon atom needs 3 equivalent bonds. And it can do that too. So for C2H4, each carbon atom needs 3 equivalent bonds, and it can do that if it hybridizes in the sp2 hybridization. So let's draw that, right? So these are the original orbitals of carbon, and they will go to 3 sp2 orbitals. Notice I can put 1 electron in each, ready for action, ready for bonding. 1 electron in each of these equivalent hybrid orbitals, sp2, and I've got 1 left over. Oh, 1 left over. But you see, the 1 left over is a p orbital that didn't get in on the hybridization, but that's okay. That's okay. These are p, right? So this is s and this is p, 2s, 2p. And that's a p orbital right there. Those are my hybrids, and that's a 2p orbital. There's another 2p orbital on the other carbon. Also got left out. Now, I only needed 3 because, you see, I formed this nice spatially maximized to minimize repulsion, right? Separation maximized to minimize repulsion. So it's a planar. Oh, but it's planar for another reason. because each of these carbon atoms has a p orbital, and we know that two p orbitals can form a pi bond, right? And I have a picture of that. That's exactly what they do. So this is the sigma. The hybrid orbitals are sigma, right? Because they're along the axis, and look at them. If I look down this axis, I can draw a circle, and there's full cylindrical symmetry, right? But I've got this leftover p orbital here on each carbon atom. That's that one there. And I didn't need it to do this, but it's still there. And so it forms a bond. It forms a bond, right? It forms a pi bond. So that p with the p from the other one forms a pi and a pi star, right, in the MOs, and you occupy the pi with the two electrons, and that's a bond. So in this, you've got a bond from this that's above or below. In this orientation, it's above or below the plane, and you've got a bond from this. So you've got a double bond. That's exactly what we know already, but we know so much more now. We know so much more because now we know that it's not just two bonds and 4 electrons. We know that they have shape to them. We know that they have structure to them, and we know that those bonds are different. These are pi bonds, and that's a sigma bond, right? And you also know why this molecule stays planar. Because if I try to twist it, then those p orbitals won't align, right? It's like a little spring. If I try to twist it, it's going to go right back, because its minimum in energy is when these things can maximize their overlap, right? So that's going to stay planar, okay? Now, and so for this case, you've got a double bond. So this is double bond, and I think I have a little carbon-carbon double bond, and I think I've got a video to show this, because this is another case where, again, I just want to make sure you guys get the intuition here, and I thought this was a pretty cool animation of sp2. So I'll play it for a minute.
2s and 2 of the 2p orbitals hybridize. Consequently, this
cool
hybridization is termed as sp2 hybridization.
Look at that.
The hybridization leads to the formation of 3 equi-energic sp2 hybrid orbitals. As you can see, each sp2 hybrid orbital is bilobed, one lobe bigger than the other. The half-filled p orbital, which was not involved in hybridization, lies at right angles to the plane of the equilateral triangle. Now, let us understand how this hybridized state results in the formation of a double bond. For this, imagine a similar sp2 hybridized carbon atom approaching this carbon atom. As these atoms come closer, an orbital overlap takes place
exactly
along the
what it's like.
internuclear axis. This bond is called a sigma bond. At this stage, the unhybridized p orbitals, which lie above and below the plane of the sigma bond, also come very close to each other and overlap laterally, resulting in the formation of a pi bond between the two carbon atoms.
All right, okay. So I thought about it. I watched that movie, of course, many times over the weekend. And I thought about, can I animate, the electrons like that and do the whole, and I think I could, but I don't know that it would be a good use of our time. So I thought that they did a pretty good job of bringing it to life. Now, this is a great time for me to tell you about why this matters. And of course, the sp2 carbon atom matters because of drinking water, of course. And this is a well in a district in India where more than 50% of the wells exceed the WHO limits for arsenic by around a factor of 5. 1.8 billion people in the world drink fecally contaminated water on a daily basis. 600 million people boil their water in the world. Boiling doesn't help with arsenic, though. Arsenic just stays in the boiled water. It kills bacteria, but it doesn't help with toxic elements. If you look at the world as a whole, and you look at sort of where there are water crisis, where the water crisis is at this level, it's a little over 3.5 billion people. And in those countries, almost 185 or so countries, where this is a serious problem, if you look at the cause of disease and the cause of death in those countries, 70 to 80% of all disease and almost 30% of all death can be attributed to the water quality. Right? So when I talk about water as a problem, I really mean it's a serious problem. It's a problem of life or death. Now, this is to get fresh drinking water. If you look at the planet and you say, well, where is the water on this planet? Where is the water on this planet? I like this picture because we consume water volumetrically, not in an area, right? We use water as a volume, and this is the water we have on this precious planet as a volume. This bubble here is all of the ocean water. Right? It's about 97% of all the water. That bubble there is fresh water that is inaccessible. Right? It's frozen. And this one here, you can't really see it. There is another dot there. That's less than 1% of the world's water. That is our drinking water ecosystem. That is what we are destroying. But see, so there's a lot of things we can try to do about this. Right? One of the things we can try to do is to see if we can tap into this in a way that's more affordable and more efficient. Because there's a lot of water here, right? And use that. But the problem is if you look at the cost of desalination today, as opposed to the cost, that's desalination. If you look at the cost of that as opposed to just digging water out of a well, like the one I just showed you in India, it's over a factor of 10, right? Still. And in fact, one of the big issues with desalination isn't just the total cost or the operating cost, but the capital cost. How do you build this plant in the first place, right? And so it takes too much money. If you look at the thing that's at the heart of desalination, it's a filter, right? It's a filter. And I talked about this in my last Why This Matters, when I talked about separations. And I promised that in my next Why This Matters, I talk about water, right? Which is what I'm doing. If you look at a desal plant, this is one of the world's largest. This is a plant called the Hadera plant in Israel. And you look at what their costs are. Remember the cost? Half of that cost, almost half of the cost is in just energy. And almost all of that energy is in pushing salt water through a filter, through a membrane. That's called a reverse osmosis membrane because you're going against the osmotic pressure. And if you look at the membrane itself, this is a picture of it. It's actually a very small layer on top of this active layer that does all the work. It's not a very good design. In fact, membranes for desalination are pretty bad, right? They kind of do everything worse than they should, except that they work, which is good, and they're cheap, $1 a square foot. But see, they take much more energy than you need. They foul up very easily, and then that means stuff gets kind of, stuck in them, and then you can't take it out. You can't clean them because these polyamide membranes, which is the same polymer used in these membranes for 50 years, haven't changed the material. Those polyamide membranes are destroyed by chlorine. So even in a desal plant, if you have drinking water in your feed stream, drinking water has 6 parts per million chlorine. That's not much. They still will go through the cost to remove it. They will remove it from the feed. Why? Because if you leave that little amount of chlorine in the feed, these membranes get destroyed. By the way, there's 40,000 of these membranes in this plant. Each one is 2 meters long and 40 square meters of area. So these are so delicate that you can't really clean them well. And that's part of what the cost of a plant involves, right? That's part of what the cost of a plant involves. Now, this would be like a plant, right? You have seawater coming in, and then you've got your membrane module that's taking the salt out of the water, and then the product water. But because this filter is so delicate, there's the picture. Because that filter is so delicate, you actually have to add a whole lot more to the plant. So much of a desal plant is built around essentially protecting this membrane. So that's cost. That's cost, right? A better membrane could change this. But like I said, the membrane, oh, there it is. You can't Snapchat on that. Snapchat? What is it that people do today? Not Snapchat. Yeah, Snapchat. Yeah, okay, thank you. You can't Snapchat on that, that's what I meant. I know it's not MySpace, but I don't know. But anyway, this is like, when I look at membranes today, as a materials scientist, materials chemist, I look at membranes, I think, that's what it looks like. Why? Doesn't have to be the case. We can do so much better. And so, okay, energy and cost goes into pretreatment, secondary treatment, and this is where this comes back. This beautiful material that we have now understood more than we did before. Because remember, before I showed you graphene and I showed you benzene. And we talked about it as a Lewis resonance structure, remember? Right? A Lewis resonance structure to help explain how it graphene does not have alternating bonds. Remember, that's what we talked about before. It's a Lewis resonance structure. So it lowers its energy by having two sets of structures that have sort of alternating bonds. We talked about it in the context of benzene. But see, now you know so much more. You know so much more. Because now you know why graphene is so special. You know why graphene is so special. It actually is the hybridization. It's the hybridization, because on top and on the bottom of a single atom of a single sheet of graphene, you've got pi bonding all the way. Those pi bonds are going across the whole surface, and those electrons are critical. Those electrons that occupy those pi orbitals are critical to the very special properties that graphene has. Right? So you now know the secret. It's sp2 hybridization, and this has allowed us. You might tell, I'm kind of passionate about this problem. Partly I'm passionate about a lot of problems, but also we happen to work on this, and we have been developing this. This is like the ultimate membrane. I can soak this in chlorine overnight. I can put it in negative pH solutions. I can heat it up. It doesn't degrade. And we have figured out how to poke holes in it at just the right size, or to stitch it together so that maybe you can filter particles by the flow in between these sheets, right? And this material as a membrane is so promising that we've actually started to commercialize it as of the last year, right? And I think this is really going to make a big difference in a lot of areas. Why? Because of sp2 hybridization. That is why. That is why this is such a special material. Okay, that's why this matters. Now, we did C2H6, there it is. We did C2H4, there it is. Look at that extra pi bond, not atomated this time. And of course, you can go on and you could do C2H2, and you can imagine what happens in this case is what you would expect. Because now I've only got, see, each of these carbon atoms only needs 2 sigma bonds, one to the hydrogen and one to the other carbon. So it's only going to grab one, it's only going to hybridize to make those 2 equivalent sigma bonds. It's only going to hybridize with one of the p electrons. So that's sp. That's sp hybridization. But notice that in C2H2, now I've got 2 p orbitals left over on each carbon atom. And so you can imagine that with these 2 p orbitals, well, you know this already, right? When we talked about p orbitals, we talked about how, you've got this, right? Okay, that's supposed to come like out of the plane and into the plane. They're orthogonal. Right? And so 2 of them are coming at the other atom. One is like this, and the other is like that. And then the other atom has one like this. And one, well, it might not at first, but then when it sees those, it's like, hey, wait a second. If I do this, we can pi bond. Right? The other ones are like this, and they pi bond, and so you get a carbon-carbon triple bond. Right? You get a carbon-carbon triple bond for C2H2 with sp hybridization. Now, it's not, there it is, right? Okay. Forms pi bond network, forms sigma bond network. It's not just carbon that hybridizes. Carbon is a classic example. But, if you look at BeH2, it's the same thing. BeH2. Well, Be starts with an can I raise this up? Be starts with orbitals that don't look like they're going to give me the equivalent 2 sigma bonds. Be starts with these s electrons filled, right? But if Be had something more like this, if it had an sp electron in each of those orbitals, well, now when I see the 2 h orbitals, the 2 1sh orbitals coming at me, I can form those equivalent bonds. So BeH2 will also hybridize to make that molecule. And all sorts of other things. The d orbitals can get in on the action. Right? So here's SF6, which we talked about. We drew this Lewis structure. Took a long time to draw those lone pairs. But now you know that the way this actually works, because those are equivalent bonds. So the only way this can work is if I form hybrid orbitals. Right? Right? But they didn't have to be equivalent bonds until we learned about Vesper. And it said, no, I want to maximize my separation to minimize repulsions, and so then we know that if they're equivalent bonds, the energy of the system will be lower, right? And so that's going to have to take some d orbitals and create these hybrid orbitals. Look, they're beautiful because now this thing from the sulfur, this thing can say, hey, I can take 6 of you and I can be equivalent bonding to all of you. That's what hybridization is. Okay? It's written right up there. We're just keeping on saying the same thing. Okay? Now, I think that I got very excited about the water, so I have to throw some t-shirts out. And now, where do I, okay, I don't go there. I don't go there. I gotta go back there and back there. And, oh, that's very loud. Okay, and right there. And right there. See you guys on Friday.